Hey folks, welcome to the Ackee Blockchain Yellow Paper course. This course was originally composed of 3 chapters. So in the first one we talked about Solci Select, Ethereum Background, Solci.js, and Remix. However, after reviewing those 4 chapters, I realized the Solci Select and Solci.js part weren't as strong, so I've deleted those, so you just get the best content. First chapter was recorded in October 2021. And the next 2 chapters were recorded in the same week in December 2021. However, 99.99% of the content is still absolutely relevant, and I hope you enjoy the course. We're making it 100% open and free. And without further ado, let's get to the course.
Let's talk about Ethereum. So the Ethereum white paper defines Ethereum as one of the subchapters, a next generation smart contract and decentralized application platform. A very brief history. The white paper was published in 2013 by Vitalik Buterin. The white paper is semi-formal. There's also a formal version of the Ethereum protocol in a sort of mathematical notation. It's called the Yellow Paper, and the main author of that was Gavin Wood. Ethereum was first released, the first block was mined on July 30th of 2015, and this version that was first released is known as Frontier. If you want to know more about Ethereum history, I recommend a book by Camila Russo called Ethereum Machine. It's very well written in a very engaging manner. If you're familiar with other blockchains, then you'll be familiar with the high-level review of how Ethereum works, but nevertheless, I have a slide here about that. So users use the elliptic curve digital signature algorithms, private keys to sign transactions. Once they get to a node, then these transactions are gossiped about to the network by these nodes. Miners collect transactions and propose blocks. And of course, there's some random process in terms of which block becomes part of the chain. And that's pretty much it. So in terms of the state transition function, so there's 3 main ones. The relevant part here is that not every block is accepted in the blockchain. The block has to be validated, has to satisfy some predicates. So there's capital Pi, as it is called in the yellow paper, representing the block level state transition function, and it's composed of capital Epsilon, which is for every single transactions state transition function, and capital Omega, the block finalization function. EVM is the execution environment for Ethereum transactions. There are 3 main data structures: the stack, the memory, and the only persistent one, which is the storage. You interact with these data structures with opcodes. They can be represented or categorized in 3 major ways. So there's arithmetic predicates and functions, as well as bit functions, so all the mathematical stuff. Then environment information, and what the yellow paper calls system operations, like calls to other contracts. Now there's other ways to categorize opcodes, such as whether or not they change state. Opcodes use stack elements from the top of the stack as arguments, so how many stack elements they pop and use or eat, and how many they push. Of course, they push the results onto the stack, as well as the gas costs. There's some exceptions to the Ethereum network, in particular at addresses 1 through 8. There are what are called precompiled contracts. So right now we're discussing the Frontier version of EVM, the very first version, and there the first address at address 1 holds EC recover for the elliptic curve digital signature algorithm. Furthermore, there is some hash functions, and at the 4th address we have the identity function. So that's rarely used these days because call gas costs went from something around like 20 or 40 to, I believe, 700 or 800. But the original intention was that it is actually used to copy memory segments. So we'll see this in more detail in the yellow paper, but it suffices to say now that when you make a call, you specify the data in terms of the memory location that you wish to pass to that call, and you specify or can specify the memory location where you want the result to get pasted into. And so the identity precompiled contract, which would just return whatever was passed to it, was intended to be used to copy around memory. So the Ethereum improvement proposal is a process that was modeled after BIP, Bitcoin improvement proposals, which itself was modeled after PEP, the Python improvement proposals. And it's a proposed change to the protocol, and they get merged in a hard fork. So far we've talked a lot about Frontier, the first version of EVM. So in March 2016, Homestead was merged. The main two EIPs were EIP2, which increased the contract creation transaction cost, gas cost, to 53,000, as well as a new opcode which corrected some of the bugs in call code. And we'll see its semantics in the latter part of the video of the course. Tangerine Whistle was a response to some denial of service attacks that were impacting the Ethereum network end of 2016, and the main EIPs were actually just one, which increased the gas costs of these very compute-heavy intensive operations. Fun fact: while researching this this video, I actually found a spreadsheet which is actually the it's the motivation for the gas costs of various opcodes. So we can see the compute time in microseconds, as well as for some of the stateful operations, the Merkle trie size, and for example, the state in bytes that it's creating, for example, for storage add, or deleting, for example, for storage kill. And then here on the right hand side, we have some coefficients for how much these things should be priced, and as a result, that gives us the intended amount of, or the total amount of gas that should be charged for such an operation. It seems that this table is very old, so I've already mentioned storage add, so there's no such thing. It's called store. Also, no such thing as storage kill, so that's done by just storing to 0. In line with copyright, I did not sort of just copy paste everything, but I wanted to keep a link in case this one goes down. So I used the Google Sheets graphical interface to create a copy, so that this link is under my drive, and it's probably going to work even if by any chance this goes down. Spurious Dragon was merged also at the end of 2016. It was also a response to DOS transaction spam. The main EIPs there included chain ID. So this was actually in response to, somewhere in between there was this incident called the DAO, which you probably have already heard of, and a hard fork to remedy that. I did not include it here because it doesn't necessarily have so much to do with the Ethereum virtual machines semantics. And in order to prevent replay attacks, then chain ID was added for transaction signing. There was also some state tri-clearing. We'll see this later on in the yellow paper. So accounts don't have to be empty. Now they can also be non-existent / deleted, and the gas costs change based on that. It also limited the contract size. This is because some of the system operations have sort of a constant cost, like call, yet in terms of storage requirements, if contract size is very large, then the disk read will be different. And so in order to limit that, the contract size was limited, which actually happens to this day. Byzantium added revert. So revert is extremely useful. In the past, exceptions were implemented by returning with an out of gas error. And the disadvantage of that was that number one, all the gas was consumed, and number two, you couldn't provide an error message. So revert changed that. There was also return data copy and return data size, in particular a new return data data structure, buffer that you can copy from, as well as a static call, which is a call that cannot change storage. In Constantinople, there were some bitwise arithmetical functions added, as well as a new create opcode and the ability to get the code hash of an external account. The Blake2 hash function was added at address 5 in Istanbul. Chain ID opcode became available to get the current chain ID, as well as adding a self-balanced opcode and further increasing some of the IO gas costs. Now, ever since Istanbul, there have sometimes called St. Petersburg, because there was a last-minute change to Istanbul, and then the last-minute version became called Petersburg. There have been 2 hard forks, Berlin and London. In terms of the naming, so you can notice that at the beginning it was kind of random. Then I believe this was the sequence of historical names for the city we call Istanbul, and then it starts to go by DEFCON cities, so DEFCON 0 and DEFCON 1. Now I haven't included these because the yellow paper, which we'll be discussing next, is actually not up to date with these hard forks, and so we will actually discuss them after we discuss the yellow paper. Here are all the major hard forks at a glance. And without further ado, let's talk about Remix. For education purposes, and not just for those, Remix is very useful. I would not recommend using it in place of an IDE. However, for educational purposes, and even later on when you want to test something or you want to demonstrate something to a colleague or to a client, it can be very useful. So they recently added sort of some IDE features that were not available before. We're probably just going to stick to this test file that I created earlier today. Supply some nice formatting. I was actually going to write it again, so maybe let's do that. So let's write a contract. And from next lesson, we're going to be looking at the yellow paper. So Remix is a great place to play around with assembly code. So for example, here, the way assembly code works is if you want to reference stuff in scope, then use sort of this operator for assignment. If you want to create new stuff, then you use the let keyword. However, anything that's created in assembly will not be available afterwards. So let's use the So I've already selected auto compile, and that should compile the file. You then go to this icon and you can, since we have modified this function as pure, then if we actually do something, so pure and view functions, we get the result immediately. It's actually probably not executed on the local blockchain, reason being that since it doesn't modify state, then it does not actually have to be a transaction on the blockchain. So let's have a look at some of the stuff I explained. So for example, if we don't name the return variable, and then we get a compile error, we can do it as such. We do it like this, we get a compile error. And so great. You can also delete all of your instances with this button. You can also select your environment. So you can use, for example, MetaMask for something like this. You can also connect it to, for example, Ganache running locally. You can specify the gas limit. You can specify how much value is sent with the call, and a lot of other options, which I'm sure you can explore. What I do want to show you is the debug option. So this is the part that is very, very useful. So you can go to the very beginning, can click here, and on my machine, I can just press space, and it goes through all of the opcodes. You can see the main data structures of stack and memory right here. For example, here, right now, the stack has 2 elements that are both empty. So you probably know EVM is a 32-byte word machine. Each stack element has 32 bytes memory. So Solidity uses these the word from 040 to 060. So this is going to be one word. 2 of these fields are going to be one word as the free memory pointer. So we can see right now it points to 80. This is, of course, in hexadecimal, so that's that. If you're wondering what these question marks are, it's trying to interpret the hexadecimal value as ASCII or Unicode string. We see a lot of more information here, the available gas and global variables. Full storage changes and storage completely loaded also tends to be very useful, but of course you can get, for example, the pre-images or like the keys for mappings and arrays due to the way that they're implemented on the EVM, which is through hashing, which we'll have a look at later. One thing that I like about Remix is that since it's in a browser, then it's in some ways hackable. So you can probably do something like this. And now we've hidden it. You could also delete it. There we go. So it's happened to me in the past, that like a few years ago, that Remix wasn't working well, or like some of the stuff wasn't working well. So you can drag around these HTML elements so that it fits the appearance that you want it to have. Of course, as I discussed, this is the next opcode, the one step of the machine, and there should also be language support for sort of linking the opcode you're on with the Solidity code, and then that way you can step through the entire program, see what's going on, and see the semantics of all of the opcodes. We just finished having a quick look at Remix. It's a great way to play around with the EVM as we're reading the Yellow Paper and as you're learning about this stuff. Last but not least, we have a list of exercises for you to try, that you can have a go at and you can check out. This concludes the very first lesson. In the next one, we're going to be talking about the Yellow Paper. We will begin it and we will begin reading through it. Hi folks, welcome to lesson 2 of the Solidity Security Engineering course. So first of all, originally I was going to also discuss a few appendices. Let me open the Yellow Paper. So I was also going to discuss RLP, which is essentially a serialization algorithm for arbitrarily compound data. So we can also serialize trees and structs. It was invented by Vitalik when he was like 19 years old. And I was also going to discuss hex prefix encoding, which they describe as an efficient method of encoding an arbitrary number of nibbles. So we'll be working a lot with data. 1 byte can be represented as 2 hex characters, and each one of these is called a nibble. So each hex character is 2 to the 4 possible values, and so 1 byte is 2 to the 8. Modified Merkle-Patricius tree, also I was going to discuss this, but basically the long story is that I won't be discussing these three because essentially I've realized they're a huge time sink. So we'll just be looking at the part of the yellow paper that is absolutely the most relevant. We'll cover about 75% of the yellow paper, particularly all of the EVM stuff. So the yellow paper itself is the full specification of the Ethereum protocol, and so it also includes all these algorithms, as well as a lot of the stuff about blocks and mining and consensus and difficulty. And that stuff is less important for a smart contract auditor. So we'll be looking at the stuff that is 75% that is the most important. That said, if you do want to have a look at these, then these two chapters are relatively understandable. Modified Merkle-Patricius tree is pretty difficult to understand from this sort of functional declarative algorithm. There's also a chapter on the Merkle-Patricius tree in the ETH wiki, which used to be on GitHub, but recently moved to their own sort of JavaScript front end. It's a slightly better explanation, still not perfect. So if you do want to read about this, then you might find probably a better resource online, which I don't know about. Maybe I'll say two things about the Merkle-Patricius tree, or three. So the first is, what is it actually used for? Well, essentially you can think of it as, let's see if they describe it in the first paragraph. Modified Merkle-Patricius tree provides a persistent data structure to map between arbitrary length binary data. It is defined in terms of a mutable data structure to map between two 56-bit binary fragments and arbitrary length binary data, typically implemented as a database. So this is really the only thing that's important for sort of high-level understanding. It's just a way to serialize a mapping between two byte arrays. So for now, I encourage you to think about it in that way. It's just a mapping between two byte arrays. It's a question I get asked is, what's this trie? So sometimes prefix trees are called tries. If you look up trie on Wikipedia, then it actually tells you the idea was independently described by Edward, who coined the term trie after the middle syllable of retrieval. So retrieval means to get something, to retrieve something, to get it. And so that's how he coined the term. These MPTs, Merkle-Patricius tries, are used in Ethereum in 4 places. So very soon we'll learn that every block has, I think, 4 components. One of those components is the header. And the header actually contains 3 roots. And of course, if you know something about tries, then the root of the tree sort of defines the entire tree. And so if the header contains the root, then we can be cryptographically assured that everybody has the same values as the leaves of the tree. And in particular, it's the state root. So we'll be looking at the blockchain state very soon. It's a mapping between addresses, 160-bit addresses, and sort of their components. The transactions root, so this is going to be a mapping between the transaction index and the transaction itself, which is RLP encoded. And the receipts. Receipts are also mapping between the transaction index and the receipt. So notice that these 2 tries are sort of different in terms of different values, but actually the number of elements in these 2 has to be the same. So every single transaction has exactly 1 receipt. And last but not least, there is also, each account has a storage trie. So, on some abstract level, that's part of the state. Because as we'll see in a second, in the state, every account has a storage field, which in this case is going to be a mapping between bytes 32 and bytes 32. and that is represented with the root of the trie as the storage trie or the storage root. We can of course see very clearly that all four of these tries, the storage trie and the ones in the header, are conform to the definition, which is their mappings between arbitrary length data and arbitrary length data. So here the key is bytes 32, the value is bytes 32. Here the key is an account, so 160 bits, and the value is going to be the account, so it has about 4 components, and they're all actually fixed length. And then for transactions and receipts, it's going to be also some compound data. I believe they're on some abstract level unbounded, both of these, because receipts also include logs, and you can technically have a lot of logs. And then the transaction, of course, includes, for example, the call data, which can be very, very large. The last thing I'll say about the Markov-Patricia trie before we jump into the yellow paper is I actually think it's a little bit poorly named. So if you do end up reading this, leaf corresponds to this row, extension corresponds to the second row, and branch corresponds to the third. It's slightly poorly named. Leaf is fine, but if you think of a tree, then the branches of the tree they call extensions, and then sort of the branching or the forking or the fork, they call that branch. So I think it should be renamed. It should be called branch, and it should be called branching or fork. So hopefully that helps you in understanding. So let's begin. Now, as everyone knows, the first rule of academic papers is you skip the first chapter. So we're actually going to skip the first few chapters. Block, state, and transactions. Having introduced the basic concepts behind Ethereum, we'll discuss the meaning of a transaction, block, and state in more detail. So this chapter is composed of 3 sub-chapters, and essentially for each of these, they'll define the corresponding field. So these are essentially structs. This is essentially a mapping between 160-bit addresses and an account, which is a struct. So we're going to define these. The world state, which is going to be denoted with lowercase sigma, is a mapping between 160-bit identifiers called addresses and account states, a data structure serialized with RLP. Though not stored on the blockchain, it is assumed that the implementation will maintain this mapping in a MPT. The trie requires a simple database backend that maintains a mapping of byte arrays to byte arrays. We name this underlying database the state database. So for example, Go Ethereum, the official Ethereum client in Golang, uses LevelDB, which is a database built by Google, and it's essentially a key value store. So it uses that as the underlying database for the trie. This has a number of benefits. Firstly, the root node of the structure is cryptographically dependent on all internal data, and as such, its hash can be used as a secure identity for the entire system state. So they're selling us on the advantages of MPTs. Secondly, being an immutable data structure allows any previous state to be recalled by simply altering the root hash accordingly. Since we store all such root hashes in the blockchain, we are able to trivially revert to old states. The account state, sigma A, comprises the 4 fields. So this is very important. These 4 fields are what every account in Ethereum has. Now in Ethereum, there are 2 types of accounts. There are contracts, and there are what are called externally owned accounts. So contracts have code, and of course they may have storage. They'll probably have storage. When a contract is created, its nonce is immediately set to 1. And for contracts, the nonce represents how many other contracts they have created. So if it's set to 1, then it will be 2 after it has created the first contract. Externally owned accounts are defined as those that don't have code. They also won't have storage. Now, I think, so for externally owned accounts, the nonce is initially 0, and it's going to be set to 1 after the first transaction. So for externally owned accounts, the nonce represents how many transactions that account has initiated. Now, it's not very well named in my opinion. I think it's poorly named, externally owned account, because for an account that doesn't have code, we still aren't sure that there does exist a private key that can unlock this, or that somebody knows of that private key. So a subset of this set would be a set that I call sort of accounts that have been the origin of a transaction. This set itself should probably be called something like, potentially external. There we go. Nonce. Oh, and last thing, the nonce that I've been talking about, and its definition is different for the two account types. It's of course completely different from the nonce used in the proof of work algorithm. A scalar value equal to the number of transactions sent from this address for externally owned accounts, or in the case of accounts with associated code, the number of contract creations made by this account. For account of address A in state sigma, this would be formally denoted sigma A sub n. Balance, a scalar value equal to the number of way. So a way is, I believe, nano is the right prefix. It's a nano ether. It's 1 to the times 10 to the minus 18 of an ether. Formally denoted. So anytime you see in the entire yellow paper, you see sigma A sub B, you know that this represents balance, and sigma A sub n will represent nonce. Storage root. So this is where the yellow paper is a little bit quirky. It first defines the storage root, and then later on over here, it will define actual storage. And similarly with code hash, it first defines the code hash, and then over here, it will define the code. So, okay, let's first read it. Storage root, a 256-bit hash of the root node of a MPT that encodes the storage contents of the account. So storage, as we know, is a mapping between bytes 32 or 256 bits. Encoded into the trie is a mapping from the Ketchak bit hash of the 256-bit integer keys to the RLP encoded 256-bit integer values. The hash is formally denoted sigma AS. So what might also be important is that we're actually taking the hash of the key. So this is relevant, for example, in Remix. If you look up the storage field, I believe it gives you the pre-image, but then it also gives you the hash, and then it gives you the value. Code hash, the hash of the EVM code of this account. This is the code that gets executed should this address receive a message call. So this is very important. So code is a byte sequence, and it consists of instructions that are enumerated in Appendix H. And every time the contract is called, so every time it receives a message call, the code gets executed, the program gets executed. Now, Solidity does do function dispatch, which is essentially an algorithm that, so Solidity has this concept of ABI encoding, which allows you to call functions in other contracts. So the first rule of ABI encoding is that the first 4 bytes of the call data to another contract will be the first 4 bytes of the hash of the function signature of the target function. Okay, so if we want to call some contract c.ping, then what we'll actually be doing is calling contract c with And now let's go to Ketchak. 1 byte, 2 bytes, 3 bytes, 4 bytes. So this is what will be happening. So we'll have call data composed of 4 bytes, and that's going to be the first 4 bytes of the hash of the function signature of the target function. This is very important. Once we call it, the target contract gets executed, and if it's a Solidity contract, Solidity performs this function dispatch based on the message.sig, which is this. It's also the first 4 bytes of message data. It will jump to the corresponding function, in our case ping, and execute it. Maybe the last thing to say is this is sometimes also called the method ID or the function ID in various tooling. Code hash. The hash of the EVM code of this account, this is the code that gets executed should this address receive a message call. So what's a message call? Well, there's 2 types of transactions. There are, we have it here. When the destination is non-zero, it's called a message call transaction. And as we'll see, the gas cost is 21,000 plus the gas cost for call data. Let's write it like this. And when 2 is equal to 0, or as the yellow paper specifies, it's an empty set, then it's a contract creation transaction. And that costs 21,000, but it also costs the cost of a create opcode, which is actually 31,000. So the total cost is 53,000. This was added later in an EIP when they realized that contract creation transactions are undervalued because they didn't sort of include the cost that you have to pay when you create a contract on the EVM lever. Now, both of these types of transactions can also create new message calls, and that's a sort of, if you call another contract in Solidity, it's called a message call. Both of these can, of course, also create new contracts through the EVM, through the create opcode. Now, as we'll see later on, the contract creation transaction executes what's called sort of deployment script or deployment code. This is distinct from, sometimes we use the word deployment script for sort of the JavaScript deployment script. Here I'm going to be using it as the deployment code. The deployment code gets executed in the context of the EVM, and it's only whatever it returns that will be the code of the contract. And the code of the contract cannot ever change except for one exception, and that is self-destruct. So in other words, this is a lie. It's not immutable. It can be nulled through self-destruct. Unlike all other fields, blah, blah, blah. All such code fragments are contained in the state database under their corresponding hashes for later retrieval. This hash is formally denoted sigma A sub C, and thus the code may be denoted as B, I guess for bytecode, given that the hash of B is sigma A sub C. So here we first define the hash, the code hash, and then we define the preimage. Now we're going to actually do the same thing for storage. Since we typically wish to refer the trice root hash with the underlying set of key value pairs stored within, we define convenient equivalence. So this try is obviously the function that's defined in Appendix D, and it's actually defined to return the root hash. So we have the storage and some mapping over the storage, and it's returning the storage root. The collab function for this set of key value pairs in the try, L sub I star, is defined as the elementwise transformation of the base function Li, given as Li of any key value is equal to Ketchak of the key, and then RLP encoding of the value. So what we're doing here is so this S in plain text is the storage root, just as here C in plain text is so they represent hashes. And then when it's bold, for example here B, it represents the preimage. So when it's bold here, it represents the key value mapping. And so we're going to map over all of the keys and values, and we're going to get this tuple. And then when we place that into the tree, the root hash of that is going to be the storage root. Now, this is kind of important. So the yellow paper doesn't, I don't think it explicitly says that anyways, but whenever, so B is the byte array, byte string, byte sequence. So this is 32 bytes. So whenever it's byte sequence, implicitly, it's going to be padded. So for example, the very first storage slot in an EVM contract or Solidity will not be, at the null string. It's actually going to be at 0, 0, 0, and you need many of these zeros. So maybe for some intro. So if I put something like 5 seep, it's going to be the same hash. Wait, let's switch to bytes. DBB. It's going to be the same hash as 0, 5 because the hash function works on the level of nibbles. Now let's go to IPython. So I've defined some helper functions. We're in Python 3.9. So I have hash denoted as H, which is catch-ack, and I have B, which converts a string into bytes. So in Python, you can sort of override built-in operators, and particular string class does that. So you can do something like 0 times 63, and it's actually going to give us 63 zeros. And if you add 1 to it, it's going to be string concatenation. So for example, this right here will be the slot of the, I guess, second storage slot since there's a 1. So let's check that with Remix. I have a helper function CB, which copies to clipboard. Sorry, not a Remix. So here we have B10E, B10E2. Notice the padding to 32 bytes. It shall be understood that sigma A sub S is not a physical member of the account and does not contribute to its later serialization. Fair enough. So the struct has actually fixed length because all of these are fixed length since we're just taking the hashes. If the code hash field is the catch-ack hash of the empty string, then the node represents a simple account, sometimes referred to as a non-contract account. So this is what is called an externally owned account. Thus, we may define a world state collapse function ls. So ls is equal to p of a for all accounts that are not the empty set. This is the empty set in mathematics, where PA is equal to the catch-ack of the address and the RLP encoding of the struct. This function, ls, is used alongside the try function to provide a short identity hash of the world state. We assume for all A such that sigma A is not the empty set, or A is in bytes 20, and V of sigma A, where V is the account validity function. This is very important. So this definition right here, I think it's poorly named. Let's start with dead. An account is dead when its account state is non-existent or empty. So in mathematics, this is the empty set. So this should be referred to as empty. Empty is a predicate that is actually defined as all of the fields being empty. So this should probably be called something like element-wise empty. An account is empty when it has no code, 0 nonce, and 0 balance. Even callable precompiled contracts can have an empty account state. This is because their account states do not usually contain the code describing its behavior. So when you call an address, an account on Ethereum through a message call, we said the code of that account gets executed, if any. There's a few exceptions, around, 8, and they are all listed in chapter 8. They're called precompiled contracts. So there are addresses 1 through X, so I think 1 through 8. And the yellow paper now tells us that these addresses, these precompiled contracts, these contracts do not have code in the traditional sense. So this has been chapter 4.1, world state. We saw that the state is a mapping between accounts and these fields. We saw the types for these fields, and we defined a dead account. This concept is actually new. It was added in EIP when a long time ago when Ethereum was suffering from denial of service attacks. So on the physical level, this part means that the account is not stored in the blockchain. So as we'll see later on, at the end of a transaction, any empty accounts become deleted. So this will not be stored on the hard drive, and so it won't take up space. So this has been chapter 4.1, world state, where we saw the state of Ethereum and defined this function. The transaction, a transaction, formally T. So whenever we'll see sigma, it's state. Whenever we'll see T, it's a transaction. Is a single cryptographically signed instruction constructed by an actor externally to the scope of Ethereum using the elliptic curve digital signature algorithm. The sender of a transaction cannot be a contract. So this is quite important. In fact, since addresses are only 160 bits, then the security of the cryptography gets significantly reduced, and it's actually technically feasible to construct a transaction from a contract. So to have a single address that is both a contract account as code and to be able to find the private key for that contract. There's an EIP about this. We'll probably have a look at it later. But for now, it won't be cheap. It'll cost about $10 billion, but it's technically feasible. And so on the EVM level, it's actually enforced that the sender does not have code. While it is assumed that the ultimate external actor will be human nature, software tools will be used in its construction and dissemination. There are two types of transactions, those which result in message calls and those which result in the creation of new accounts with associated code, known informally as contract creation. Both types specify a number of common fields. Nonce, a scalar value equal to the number of transactions sent by the sender. So the nonce is not only part of the account, it's also part of the transaction. So what happens in MetaMask, when you send a transaction and you're waiting too long, there's a button called speed up. Now if you click that button, then it will send the same transaction, or it could even be different technically, with the same nonce. And so since a transaction with a specific nonce can only be included once, miners get to choose which of those they include, and if the second one has a higher gas price, then they'll include that one and not the first one. Gas price, a scalar value equal to the number of So I guess you can read this, I'll skip it for now. What's important is additionally, contract creation transaction contains in it technically unlimited size byte array specifying the EVM code for the account initialization procedure. So this is what I called a few minutes ago the deployment script, the deployment code. So in it is the code that gets executed in the context of EVM, and whatever it returns, that will be the code of the contract, which can never change, save for one exception. In it is the EVM code fragment. It returns the body, a second fragment of code that executes each time the account receives a message call, either through a transaction or due to the internal execution of code. Init is executed only once at account creation and gets discarded immediately thereafter. Okay. In contract, a message call transaction contains data, an unlimited size, technically unlimited, but you have to pay gas for each byte. Byte array specifying the input data of the message call, formally TD. So this I'll generally call call data. Now in Remix, this stuff is also placed into a call data field, but on the yellow paper, it's distinct. Appendix F, I think that's the one. That's the one about cryptography. Appendix F specifies the function S, which maps the transaction to the sender. So this is actually a pretty modern invention in crypto. Bitcoin doesn't have this. In Bitcoin, you have to specify the address as well as the signature. But there's in Ethereum, you can just specify the signature, and Ethereum is able to compute the sender from the signature. So the higher level API we'll be using is S, which can compute the sender of transaction. Happens through the ECDSA of the curve using the hash of the transaction as the data to sign. For the present, we simply assert the sender of a given transaction T can be represented with S of T. These L functions usually in the yellow paper, therefore serialization. So this specifies how to serialize a transaction because it's kind of just a struct. So this specifies the ordering. The only difference, so if T, this is the 2, is the empty set, it's contract creation, and then this is the message call. The only difference is here we have data, call data, and here we have the init code. Here we assume all components are interpreted by the RLP as integer values with the exception of the arbitrary length arrays. So remember when I said that B32 gets padded? So N256, which is the set of 256-bit integers, does not get padded. So this will be in the shortest possible representation. The address hash TT is slightly different. It is either a 20-byte address hash, or in the case of, I don't know why they call it address hash. I mean, an address is already a hash of a public key. So here they really just mean address. Or in the case of being contract creation transaction, thus formally being equal to the empty set, it is the RLP empty byte sequence. Okay, and thus the member of B0. So in this chapter, we discussed the transaction. We discussed its structure and its serialization. 4.3, the block. The block in Ethereum is the collection of relevant pieces of information, H, together with information corresponding to the comprised transactions, T, and a set of other block headers, U, that are known to have a parent equal to the present block's parent's parent. So these are uncles. Although here they're called omers, which is a gender-neutral version of uncle. The block header contains several pieces of information. So you can read this on your own. This is what comprises the block header. In one of the first videos, we saw that the state root, the transactions root, and the receipts root are these Merkle-Patricia tries. So it's exactly explicitly stated. The other two components in the block are simply a list of uncles and a series of transactions. So I don't think this is really correct. Later on, there was an EIP. I'm pretty sure this was through an EIP that added receipts, and actually they should probably be here as well. So for some reason they're missing. 4.3.1 transaction receipt. In order to encode information about a transaction concerning which it may be useful to form a zero-knowledge proof, we encode a receipt of each transaction containing certain information. Each receipt, denoted block, receipt, index, is also placed in a trie. The transaction receipt R is a tuple of 4 items comprising the status code. This is very important. So this is either 0 or 1. It's 1 if the transaction was successful, and it's 0 if it failed. So it's the opposite as in Unix. The cumulative gas used in the block containing the transaction as of immediately after the transaction has happened. So RU is going to be the cumulative gas that all transactions so far have used. The set of logs created are L. So L is going to be a set of logs. And then the Bloom filter, which is just sort of a helper function for the logs. We assert that the status code RZ is a non-negative integer. We assert that RU, the cumulative gas used, is a non-negative integer. The sequence RL is a series of log entries. So this stuff you can read on your own. The Bloom filter. I actually found a bug in the Bloom filter. So this is actually my code. Now it's corrected. Holistic validity. We can assert a block's validity if and only if it satisfies several conditions. It must be internally consistent with the Omer and transaction block hashes. So again, this stuff I'm going to skip over, and we'll jump straight to transaction execution. This is the first most important chapter. This was some definitions, gas and payment. 6, 7, 8, 9. So after dozens of minutes, we're finally at how to execute a transaction. The execution of a transaction is the most complex part of the Ethereum protocol. It defines the state transition function, epsilon. It is assumed that any transactions executed first pass the initial test of intrinsic validity. So it has to be well-formed RLP, the signature has to be valid, so does the nonce. The sender account has no contract code deployed. So this is the IP I was referring to that we'll arrive at later. Here you can read the justification for this requirement, and the EIP states that it costs roughly $10 billion to perform this collision. The gas limit is no smaller than the intrinsic gas. G0 is by the transaction, so we'll see in a few seconds what G0 is, and the second sender account balance contains at least the upfront cost V0, and we'll see in a few seconds what that is as well. Formally, we consider the function epsilon with T being a transaction and sigma the state. Sigma prime, so represent the new state, is equal to epsilon of sigma and T. Thus, sigma prime is the post-transactional state. We also define epsilon G to evaluate the amount of gas used in the transaction, epsilon L to evaluate the transaction's accrued log items, and epsilon Z to evaluate the status code resulting from the transaction. So I believe, and we'll see that later in more detail, I believe these are then added sort of to the receipts. Throughout transaction execution, we accrue or accumulate certain information that is acted upon immediately following the transaction. We call this the accrued transaction substate and represented as A. This tuple contains AS, the self-destruct set, which is the set of accounts that will be discarded following the transaction, AL, which is the series of logs, AT, okay. And then there's, so self-destruct, log, AR is going to be the refund balance, there it is. Increased through using store instruction in order to reset contract storage from 0 to non-zero value. Though not immediately refunded, it is allowed to partially offset the total execution costs. So if you null storage value, store to 0, you can get a refund, and that is added to the accrued substate and then acted upon at the end of the transaction. Unless I'm mistaken, self-destruct also adds to the refund balance. So this might be a little imprecise. And finally, there's sort of these accounting variables, AT, AA, and AK. And what they do is they keep track of how many accounts have been visited or touched, how many accounts have been accessed, and K is how many storage keys have been accessed. So, for example, this one is used, as we mentioned earlier, to delete from the state trie accounts that are empty. The latter two are used for gas computation mainly because, yeah. When a node loads storage, it doesn't load the entire storage of a contract, and so if it loads one storage key, it's going to be much cheaper to access it in that transaction. So that's why we need to keep track of that. Another reason is storage gets committed to persistence storage, like on the node level, only at the end of the transaction. So it's cheaper to do an store if you've already done an store on the same key inside that one transaction. These two were added through an EIP quite recently in Berlin. We define the empty accrued substate a 0 to have no self-destructs, no logs, no touched accounts, 0 refund, precompiled contracts index addresses, and no access storage. We define intrinsic gas G0, the amount of gas this transaction requires. Okay, so this is very important. So we always pay 21,000. If it's a create transaction, we also pay an extra 32,000. And then in both cases, we pay, I believe, 16 gas for non-zero bytes and 4 gas for 0 bytes of the call data / init code. And that forms the intrinsic gas. The upfront cost V0 is calculated as, so TG was the gas limit of the transaction. So the transaction specifies a gas limit. TP was the gas price. So this is in units of gas. This is in units of ether per gas or weight per gas, NTV, which is the value that we're sending in that transaction. So this will be sent to the very first target of the transaction. So if it's a message call, it's the destination, it's a contract creation, it's the contract. Now, of course, if there's internal message calls for other transaction, they can also send Ether, and it can be smaller or greater than TV, which is the value of the transaction itself. The validity is determined as, so the sender cannot be an empty account, and at the same time, the code hash, so it cannot be a contract either. The nonce has to be equal to, the nonce of the transaction has to be equal to the nonce of the account. The TG, which is the gas limit, has to be at least equal to the intrinsic gas. The balance has to be at least equal to the upfront cost. And then this one is important. This one is interesting. It's a little bit easier if you move the minus over here. So L here is the last receipt. And remember, U was the cumulative gas used in that block so far. So the gas used plus the gas limit must be smaller than or equal to the block gas limit. Here it's part of the header. Note the final condition: the sum of the transaction's gas limit TG and the gas utilized in this block prior given by must be no greater than the block's gas limit. The execution of a valid transaction begins with an irrevocable change made to the state. The nonce of the account is incremented by 1, and the balance is reduced by part of the upfront cost. So the reason they don't reduce it immediately by V0 is because that is actually defined later on in chapter 7 and 8. The TV part is defined in chapter 7 and 8 based on whether it's a contract creation or message call. Basically because you can also send value when these two occur as the result of EVM code. So they separated. This part can only occur as part of a transaction. So that's what we're going to do here. And then this part is handled sort of by the resolver, whether it's a contract creation or a message call. The gas available for the preceding computation is defined as TG minus G0. The computation, whether contract creation or message call, results in an eventual state, the change to which is deterministic and never invalid. There can be no invalid transactions from this point. So at this point, we know that the transaction may be included in the block. We define the checkpoint state sigma 0, where we decrement the balance and we increase the nonce. Evaluating sigma p from sigma 0 depends on the transaction type. We define the tuple of post-execution provisional state sigma p, the remaining gas g prime, accrued substate, and status code. So these two functions are very important. So lambda is going to be the contract creation function, and theta is going to be the message call function. Note we use theta 4 and lambda 4 to note the fact that only the first four components of the function's values are taken. The final represents the message call's output value and is unused in the context of transaction evaluation. This makes debugging very difficult. So error strings, revert messages, are also placed in return data, or here they call it output value. And since top-level transactions don't have an output, you have no way of accessing the revert string. This makes debugging pretty painful and means that you have to resort to other means, like I think it's in the notes. For example, the RPC call that Ethereum nodes support, some of them, debug_trace transaction, which gives you a huge JSON with every single instruction that got executed in that transaction. And basically what you do is you look at the very last instruction, and if it's a return or revert, then you go into memory and you decode it and that's how you get the return value. So in Ganache or Brownie or Hard Hat, when you do a transaction and you do transaction.return value, it's exactly what it's getting. It's getting the huge debug JSON, and it's just looking at the last instruction. So it's extremely inefficient. After the message call, contract creation is processed. So at this point, we dispatch it to the resolver, and now it's been resolved. So now we're at the very end. After the message call contract creation is processed, the refund counter has been incremented for the accounts that were self-destructed throughout this invocation. So I was right. Self-destructing also does increment the refund counter. Then the state is finalized by determining the amount to be refunded, G star, from the remaining gas. So basically what this equation means is that you can offset at most half of your gas costs. So this represents how much to be refunded. So for example, if this is 10,000 and your gas costs are 20,000, then you can offset that. But if they're 30,000, you can also offset that. But if they're 50,000, then you can only offset 7,500. So you can only offset at most one half. The total refundable amount is the legitimately remaining gas G prime added to A sub R, with the latter component being capped up to a maximum of half of the total amount used. So, okay, the ether for the gas is given to the miner, whose address is specified as the beneficiary of the present block B. So we define the pre-final state sigma star in terms of the provisional state, and looks like they're giving something to the miner. The final state sigma prime is reached after deleting all accounts that appear in the subdestruct set or are touched and empty. So this is the part we talked about. And finally, we specify epsilon G, epsilon L, and epsilon G, epsilon Z. So this stuff is stuff that was returned, and we specify it here. Yeah, and so these are used to help define the transaction receipt, which I guess we'll see later. Well, here's just the definition, but I'm not 100% sure where the algorithm to compute it lies. Chapter 7, contract creation. There are a number of intrinsic parameters used when creating an account. Okay, so there's also the concept of salt. This is because there's also a relatively new opcode called create2. And for create2, the salt is not the empty set. And for either contract creating transactions or just using the plain old create opcode, the salt would be the empty set. We define the creation function formally as the function lambda, which evaluates from these values together with the state sigma and the accrued substate to the tuple of the, okay? The address of the new account is defined as being the rightmost, so it's important, so it's modulo 2 to the 60 of the hash of the RLP encoding of the structure, containing only the sender and the account nonce. So, in other words, so this is for the plain old create, and in plain old create, the address depended only on the address of the creator, and which can be a contract or an external account, and the account nonce. For create2, the rule is different and is described in EIP 1014. Combining the two cases, we define the resulting address for the new account. So you can read this on your own. Let's jump here. The account nonce is initially defined as 1. So we actually saw this earlier. the balance as the value passed, the storage as empty. Thus, the mutated state becomes sigma star, where V prime is the account's pre-existing value in the event it was previously in existence, right? So I don't think this is actually correct. So a contract may have balance, or like an account may have balance when you deploy a contract on that account. So actually this is much more specific. It's the value we're sending plus whatever balance it had before. Finally, the account is initialized through the execution of the EVM code in it according to the execution model. Code execution can affect several events that are not internal to the execution state. So of course, storage can be altered, further accounts can be created in the init code, and also you can create message calls, so you can call contracts in your constructor. As such, the code execution function xi evaluates to a tuple and the body of the code. Okay, so in other words, we're taking the parameters that we received over here, and we're going to execute the code using the resolver, the code execution function. And we pass in the environment data. So the gas price, etc. ID evaluates the empty tuple as there is no input data to this call. IH has no special treatment and is determined from the blockchain. Code execution depletes gas, and gas may not go below 0. Thus, execution may exit before the code has come to a natural halting state. In this and several other exceptional cases, we say an out-of-gas exception has occurred. The evaluated state is defined as being the empty set, and the entire create operation should have no effect on the state. So this is important. So the yellow paper uses this notation that when there's an exception, the state that the function returns is the empty set. So the entire blockchain state is nulled, and then there's some logic that if the state is null, then it was an exception. If the initialization code completes successfully, a final contract creation cost is paid. The code deposit cost proportional to the size of the created contract's code. If there's not enough gas to pay this, we also declare an out-of-gas exception. The gas remaining will be 0 in any such exceptional condition, i.e. if the contract creation was conducted as the creation was conducted as the reception of a transaction, then this doesn't affect payment of the intrinsic cost of contract creation. It is paid regardless. However, the value of the transaction is not transferred to the contract. If such an exception does not occur, then the remaining gas is refunded to the originator, and the now altered state is allowed to persist. Thus, formally, we may specify the resultant gas state, accrued substate. Okay, so this is a little bit complicated, but let's start at the end. So F signifies whether or not there was an exception. For example, this was later added in an EIP, that the body of the code can never be greater than 24 kilobytes. Now, an EIP quite early in Ethereum's history also added the revert opcode. So revert is a little bit different because it doesn't consume all gas like all other exceptions do. So that's why you'll see in the yellow paper, F is failure or the resultant state is an empty set. This represents revert. And so, for example, this is also important. If there was a failure or if there was a revert, then the resultant state is actually equal to the first state. If there was a failure, then we consume all gas, but if there was a revert or the transaction was successful, we do not. The exception in the determination of sigma prime dictates that, oh, the resultant byte sequence from the execution of the code specifies the final body for the newly created account. Note that intention is that the result is either a successfully created new contract or no new contract with no transfer value. In addition, observe that if the execution of the initialization code reverts, the resultant gas is not depleted, but no new account is created. This section is also very important. Note that while the code is executing, the newly created address exists, but with no intrinsic body code. So this footnote is actually very important. During initialization code execution, external code size on the address should return 0, and therefore presumably external code hash will be the hash of the empty string, which is the length of the code of the account. So I believe we can find that right over here. So the account that we're creating actually doesn't have any code, at least for the purposes of external code size and external code hash. However, it does have code from the perspective of the environment. So the bytecode is equal to the init code. And so actually, the code size should return the length of the initialization code, and also code copy. Code copy instruction will also allow us to access this. Now, this is very important for Solidity. So the way, maybe let's add some more detail here. So code, or let's call it state variable initialization. So the order that Solidity, I guess E, the order that Solidity runs the code of a constructor of a deployment code is it first runs, so when you do top level variable uint a is equal to 5, that gets run before the constructor. Then the constructor is run. And so the init code on the level of Solidity, here dot is concatenation of bytes, will be first the state variable assignment, then the constructor, and then there is, except for stack manipulation, roughly the following pattern. So it usually does code copy, and it copies G, which is the contract code itself, the body. Code copy copies it to memory. So it does code copy to memory, and then it does return from memory to return the body. The intuition here is that all the instructions that end with copy place data from some store, in this case code, to memory. And all instructions that end with load place some data from some store to the stack. So load is always one word, 32 bytes, while copy is always arbitrary length. I don't think there's I know there's not a code load instruction, but some stores have a load and copy variant. For example, you can do call data load, and you can also do call data copy to access the call data store. There's also a slight interesting thing. So for call data, you can access ranges beyond its size. So for example, even if the call data is empty, which it probably won't be unless you have a fallback function, because in Solidity, as we already know, the first 4 bytes of call data is the function ID. But let's say we have a function ID, so let's say it's just 4 bytes. You can still do call data load to get 32 bytes onto the stack, and it just extends it with 0. And you could do the same thing with call data copy. In fact, you could even say call data copy, 500, even though the call data is just of length 4, and it just extended with 0. This is not, for some reason, the case for return data, which is another store in the EVM. With return data, you can never access anything beyond the length. Thus, any message call received by during this time causes no code to be executed. Okay, so from the level of external contracts, this account has no code during the initialization execution, during the constructor execution. If the initialization execution ends with a subdestruct, the matter is moot since the account will be deleted after the transaction is completed. For a normal stop opcode, which can also occur if you finish the program. So if you reach a program counter sort of beyond the code length, that is implicitly also executed as a stop instruction. Or if you just return, if you do return and you do a memory value and you do a length of 0, so you return just the empty byte sequence. If the code returned is otherwise empty, then the state is left with the zombie account and any remaining balance will be locked into the account forever. This is also true if you return anything that doesn't allow you to retrieve Ether if you sent an endowment. By the way, maybe this is a good point to mention the website ethervm.io. I strongly recommend it. It's a terrific reference for all of the instructions in the EVM and what they do. For example, we talked about cold data load and cold data copy. So let's see what they do. Cold data load takes one argument, which is going to be the offset. It looks into, it even gives you in terms of solidity variables. And then this is the stack output. For cold data copy and for other instructions that deal with memory, the syntax is usually always the offset and then the length. And if there's instructions that deal with multiple stores, it's going to be the destination offset, so the offset in memory, then the offset in cold data, and the length. For return, for example, it's exactly the same thing. So if you want to return, you specify the offset in memory as well as the length. Almost all of the instructions on the EVM we have access to in Yule, which you can get into with the keyword assembly in Solidity. And actually the variables are one-to-one. So for example, log3, the function will accept, I guess, 5 arguments, and it's going to be the same exact ones as the stack elements that this instruction eats on the EVM level. The Yule does not provide great access to stack operations. So there's no dupe and swap. I don't think there's even push. There is a pop, but it's very rarely used. The idea being that it's an abstraction, so it handles the stack for you, but it allows you to manually interact with memory, with return data, with code, with call data, and with all the stores in the EVM. Chapter 8, message call. In the case of executing a message call, several parameters are required. So far we've defined lambda over here, and now we're going to have a look at theta. Aside from valuing to a new state and accrued transaction substate, message calls also have an extra component, the output data. Okay, so on the EVM level, as we'll see in Appendix H, which defines all the instructions, when you make a call, you can, I'll actually show you. Okay, right here. So as we'll see in chapter 9, mu is the local machine. It's all the stores that are specific to that transaction execution. Mu sub s is stack, and mu sub s5 represents the 6th stack element. So, and then n is usually just mu sub s6 or the 7th stack element. So here what's going on is prime represents the new memory, so the new memory will get the output. So what's going on here? When we make a call, we can specify the memory offset and the memory length. And the output data gets placed in that segment of memory. Now, this is a problem, for example, for proxy contracts. So if you want to have a proxy contract, let's have a look at how a proxy contract looks like. Let's just go to the non-upgradable repo. I think it also has a proxy. Okay. So the fallback function just executes the internal fallback function. And that there's a hook, and then it executes the internal delegate. So what's going on here? So call data copy, call data size. So whatever is passed to this contract, all of the call data we copy to memory. So remember, this is the destination offset. So we're going to be, probably rewriting memory actually from offset 0. This is the call data offset. So from 0. Call the implementation. So we perform a delegate call. Solidity currently doesn't provide a higher level API for delegate calls, so it all has to be done through assembly. We'll see later on what a delegate call is, but intuitively, it's where you take another contract's code and you execute it with your own storage. This means we pass in all gas that is currently available. This is the destination. This is value. This is, I guess, how much, let's have a look actually. Gas, destination, args, offset. Okay, so sorry, delegate call can't do value. So this is so this is the offset in memory, and then the memory length. And then this is important. This is why I'm showing you this. So this is going to be again, the offset in memory where to place the return data. But then this is going to be the length of the return data. And now previously in the past, you had to know the length of the return data. But then you couldn't build a proxy, because with a proxy, we don't know in the general sense, the length of the return data. So this was a big problem. You couldn't build upgradable contracts in an efficient way. So then they added another store, which is return data, or sometimes called the output buffer. And so that gives you access to the return data of the very last call. And so here we actually don't copy anything to memory, and instead we handle that over here. Aside from evaluating to a new state and include transaction substate, message calls also have an extra component, the output data denoted by the byte array. Oh, this is ignored when executing transactions. However, message calls can be initiated due to VM code execution. And in this case, this information is used. So we actually saw that right here in the proxy. This is going to be the output buffer of this message call. And so what's going on here, we again overwrite memory, because right now it holds call data. So potentially overwrite, and this is non-zero. And then this is the offset in return data. This is the length in the return data. And so now in memory, we have the return data. So calls or message calls in general, they take a bunch of stack elements. They take a lot of elements from the stack. They always place exactly one element onto the stack, which is the status code. So here we're doing a switch, and if it's false, we revert, potentially with an error message. And if it's anything else, this can only be one. We do a regular return. Note that we need to differentiate between the value that is to be transferred v from the value apparent in the execution context for the delegate call instruction. So, right. So in delegate call, you can't transfer value, Ether. So this is going to be 0. But in delegate call, if you do message.value, it's actually, or whatever the corresponding instruction is, it's actually going to tell you the value of the message call that initiated that delegate call. And so that would be the value that's apparent in that execution context. In other words, what that's saying is the proxy works. So in the logic contract, if I do message.value, it's going to show me the message.value of the message call to the proxy. We define sigma1, the first transitional state, as the original state, but with the value transferred from sender to recipient. Okay, unless it's the same thing, it's very important. Throughout the present work, it is assumed that if sigma1 R was originally undefined, it would be created as a count with no code. Thus, the previous equation should be taken to mean. Okay, so this is all pretty clear. The account associated code identified as the fragment whose hash is code hash is executed according to the execution model. Just as with contract creation, if the execution halts in an exceptional fashion, i.e. due to out of gas, stack underflow, invalid jump destination, invalid instruction, undefined instruction, etc. By the way, if you want to see some of the exceptions that can occur, one of the nodes that or EVM implementations that I'm more familiar with is KEVM. And it's written through a paradigm called literate programming. So code comments are top level and code itself is fenced. So these markdowns are 100% executable. And here we go. So for example, there's a specific instruction called invalid, but then any instruction that is undefined has the same exact semantics. So these are undefined. And this one is actually the designated invalid instruction. For example, if you jump to an instruction that is not a jump destination location, if you call an instruction that takes up more arguments than your current stack, and a few others. There's actually a bug here in terms of documentation that I've yet to report. Invalid memory access indicates that a bad memory access occurred. So actually you can't do this. Memory is technically infinite, although gas costs do grow quadratically. This can happen when accessing local memory. So yeah, so this is alive. As we already mentioned, call data extends infinitely with zeros, so you actually will not get an exception. I'm not 100% sure with code copy. I'll check that after the call. So it only concerns return data where the exception actually does occur. And so it should actually be called invalid return data access and potentially code copy. On the EVM level, you have about 5 calls. So there is call, transaction, instructions that originate message calls. There's call code, which is the old version of delegate call, but it was a little bit buggy. So it's never used these days. Delegate call, and then you also have static call. So static call is very similar to the view concept in Solidity. So in a static call, if you mutate state, you get an exception. So static call ensures that the call won't mutate state. Great. Just as with contract creation, if the execution halts in an exceptional fashion, for example, out of gas, stack underflow, invalid jump destination, the invalid instruction, undefined instruction, etc., then no gas is refunded to the caller. and the state is reverted to the point immediately prior to balance transfer. Again, same thing here, or maybe not the same thing. I thought they would also be using the F function, but seems like they're not. It is assumed that the client will have stored the pair Ketchak of code and code at some point prior in order to make the determination of the code feasible. As can be seen, there are 9 exceptions to the usage of the general execution framework XI for evaluation of the message call. These are so-called precompiled contracts, meant as a preliminary piece of architecture that may later become native extensions. The contracts in addresses 1 through 9 execute, and then they list them out. So if you call with a message call, addresses 1 through 9, there's special execution semantics given by Appendix E. And if you call any other address, we go into the code execution function, chapter 9. Okay, so we finally arrived. I just went for a walk and just got back. We finally arrived at the most important chapter, execution model. The model specifies how the system state is altered given a series of instructions and a small tuple of environmental data. This is specified through a formal model of a virtual state machine. So turns out that the Turing machine assumes infinite memory. So actually all real-life Turing machines are not formally Turing machines. So they make the effort to qualify this right here. It is a quasi-Turing machine. The quasi-qualification comes from the fact that the computation is intrinsically bounded to the parameter gas, which limits the total amount of computation done. The EVM is a simple stack-based architecture. The word size of the architecture is 32 bytes, 256 bits, and also the size of stack items. This was chosen to facilitate hash and cryptographic computations. The memory model is a simple word addressed byte array. Now, this is where I differ with the yellow paper. I don't think it's fair to call it a word addressed byte array. In fact, I think a byte addressed word array would be more precise. So let's say we have some bytes in memory, and obviously one word is 32 bytes, but for now, let's assume this. So if you do mload, if you do mload, which is gonna load one word from memory and push it onto the stack, and you pass in 0, you get these 4 bytes. If you pass in 1, you get these 4 bytes. If you pass in 2, you get these 4 bytes. So I think you can see that a byte addressed word array might be better. I mean, I don't think the definition for these is specified. The stack has a maximum size of 1024. This is true in theory, but in practice, as we'll see in a second, you can only access the top 16 elements. So unless you pop from the stack, you actually have no access to the to elements deeper than this. You can also see this in Solidity. So let's have a look. So here we have 16 local variables, and as soon as you have another local variable, in this case an implicit one, then it would violate sort of invariant of imperative programming, which is the ability to be able to refer to any variable in the current scope. Solidity will give us a compile error saying stack too deep. The machine also has an independent storage model. This is similar in concept to the memory, but rather than a byte array, it is a word addressable word array. So this part is correct. It's a mapping between 32 bytes and 32 bytes. Unlike memory, which is volatile, storage is persistent and is maintained as part of the system state. All locations in both storage and memory are well defined initially to 0. The machine does not follow the standard von Neumann architecture. Rather than storing program code in generally accessible memory, it is stored separately, accessible only through a specialized instruction. The same is also true for stores like call data, return data, and in this case, code. The machine can have exceptional execution for several reasons, including stack underflows. Like out of gas exception, they do not leave state changes intact, rather the machine halts immediately and reports the issue to the execution agent. The execution agent is either the transaction processor or recursively the spawning execution environment. So this is kind of important. In Solidity, if you do a high-level call, so a high-level call is anything of this form, so a contract and a function call, or some interface over some address. These are high-level calls. Solidity in those cases will propagate the error. So if one of these results in a status code of 0, then it will also revert the current execution, the current message call. If you do a low-level call, so obviously anything through assembly or through .call, then Solidity will not propagate the error. So actually .call returns something like this. And then you have to do something like that in order to achieve the same behavior. While we're at this low-level calls, there's another difference. For high-level calls, Solidity will do an existence check. So it's going to do either external code size or external code hash to check that the contract exists. And if you do a low-level call, it doesn't do that. So you would also have to do that manually. Something like that. So this would be roughly equivalent to this if we also added the method ID here. So we could probably use ABI encode for that. I think there was one more thing I want to say. Oh yeah, the reason this is useful is if the contract doesn't exist, then this will actually return success. Said in another way, and that would be unexpected behavior. Said in another way, if you send call data to an externally owned account, one that doesn't have code, then the call data is ignored, the value is transferred, and the call is successful. Fees denominated in gas are charged under 3 distinct circumstances, all 3 as prerequisites to the execution of an operation. The first and most common is the fee intrinsic to the computation of the operation. So, secondly, gas may be deducted in order to form the payment for a subordinate message call or contract creation. This forms part of the payment for create to, call, and call code, and delegate call. And finally, gas may be paid due to an increase in the usage of memory. So we track how much memory you've used, and this gas cost grows quadratically over time. Over an account's execution, the total fee for memory usage payable is proportional to smallest multiple of 32 bytes that are required, such that all memory indices are included in the range. This is paid for on a just-in-time basis. As such, referencing an area of memory at least 32 bytes greater than any previously indexed memory will certainly result in additional memory usage fee. Due to this fee, it is highly unlikely addresses will ever go above 32-bit bounds. That said, implementations must be able to manage this eventuality. Storage fees have a slightly nuanced behavior. To incentivize minimization of the use of storage, which corresponds directly to a larger state database, the execution fee for an operation that clears an entry in the storage is not only waived, a qualified refund is given. In fact, this refund is effectively paid upfront since the initial usage of a storage location costs substantially more than normal usage. See Appendix H for a rigorous definition of the EVM gas cost. Execution environment. In addition to the system state sigma, the remaining gas for computation G, the substate A, there's several pieces of information. So I is the environment. IA is the address of the account which owns the code. So message.sender. Address this, message sender, transaction.origin, message sender, message.value, etc. Message.data. Not all of these we have access to in Solidity. For example, this one I don't think we do. And I don't think we even have access to it on the EVM. There's not an instruction that tells us whether we're in a static call. The execution model defines the function xi, which can compute the resultant state sigma prime. So here that's what it does. We now define the xi function. In most practical implementations, this will be modeled as an iterative progression of the pair comprising the sigma and the machine state mu. Formally, we define it recursively with the function x. This uses an iterative function O together with functions z and h. So x will use O, which defines the result of a single cycle of the state machine. Z determines if the present state is an exceptional halting state, and H specifies the output data of the instruction if and only if the present state is a normal halting state of the machine. So essentially what we're going to do is we're going to first have a look if there's an exceptional halt. That's what Z is going to do. If not, we're going to have a look at if there is some return value. That's what H is going to do, in which case we halt immediately. And if not, then we execute the next instruction. The empty sequence, denoted empty sequence, is not equal to the empty set. This is important when interpreting the output of H. So H will at first be empty set, but then, for example, through stop or self-destruct, it can become the empty sequence. So H evaluates to empty set when execution is to continue, but a series potentially empty when execution should halt. Now, this is important. So xi will return some values. Now, those values will be equal to this iterator function x. So initially, the program counter is 0. That's mu. Memory is all set to 0. How much memory we've used is set to 0. The stack is an empty sequence. Output is initially an empty sequence as well. And gas available is how much gas we have available. Now this is important, 139. So before we discuss 139, let's discuss exceptional halting. The exceptional halting function Z is defined as. So the first says if the gas available is smaller than how much gas we have to pay for this instruction, which is given through the gas cost function C, or okay, so let's get this one. Actually, let's not. So delta specifies how many stack items to remove, and it's well defined for every well-defined instruction, but it's the empty set for undefined instructions and the invalid opcode. So obviously, if we've reached an undefined instruction, one that hasn't been used in the current, so 1 byte is 1 instruction, but 1 byte is 256 possibilities, and there's less than 256 instructions. So there are some that are undefined. So if we reach an undefined instruction, we also do exceptional halting. The majority of these should never occur if the Solidity compiler is correct. Some of these at least. But I could be wrong, but I think the Solidity compiler, unfortunately, at least in the past, it used to use some undefined instructions as an exception, which is, that's true, that's bad practice, because these undefined instructions could in the future be defined. This is if the size of the stack is smaller than how many elements we need to remove. D, which we'll see in a second, is the set of jump destinations. And for a jump, the first parameter is the destination. For a conditional jump, the first parameter is also the destination, but however, we only jump there if the second parameter is true, is non-zero, which would be by Solidity interpreted in a Boolean value as true. So this is what I talked about earlier. Return data is slightly different from call data in that you can never exceed its length. So if we have return data copy, the zeroth element, so mu s0, will be the destination, so memory, and then this will be the offset of return data, and this will be the length, how much we want to copy. So this would be Stack Overflow. This would be if we don't have permissions to mutate state, and so this function, which we can actually see right here, is the set of instructions that mutate state. Notably, logs also mutate the blockchain state. So if in Solidity, for example, you have a function that emits an event, it cannot be viewed, which can make working with Echidna quite difficult, because Echidna, at least one flavor of it, relies on events. So if you want to add events, you got to remove the view. And finally, this is also quite interesting. So this was added, I believe, in Berlin. So before Berlin, S-Store, the gas cost of S-Store used to be roughly the following. So 20,000 to take a value from 0 to non-zero, 5,000 either to keep it the same or to take it to another non-zero value. And then if you nulled it, it would also cost 5,000, but you would get a 15,000 refund. Within UYP, it's a little bit different. So they've optimized it much more better in terms of sort of the actual costs on the node, since storage keys are loaded and they're only committed at the end of a transaction, and they're not all loaded at once. So now if you modify it this way and then you modify it again, it only costs 800 gas. So this breaks some invariants. So there's an invariant on the EVM level, or like there's a reentrancy protection on the EVM level to only send 2300 gas in certain situations together with a call. So as we can see, before 2300 gas was not enough to make any storage change. However, now if in a different message call you've already accessed the storage key, and these storage keys are accounted for on a per transaction basis, then another message call you could modify it again, in which case it would only cost 800 gas. So now S-stores are possible, and therefore reentrancies are also possible. And so to prevent that, they added another protection, which is that if the current instruction is S-store, then we need to have at least, I think, like 5,000 gas available. Great. So let's go back to 139. So if it's an exceptional halting state, as we said before, we null the blockchain, so we return an empty state, and pretty much nothing changes. Now, if the output buffer, the return data, is not the empty set, then we append it. We append the output buffer and we execute the transaction. So that is defined right over here. O is defined here, and I believe it's defined somewhere here. So if you have a stop or self-destruct instruction, as was already stated, we return the empty sequence. If it's a return or revert, then return specifies this hReturn function. So let's actually have a look at it. So it's very simple. We take return. We actually already saw it in EtherVM. So it just takes the memory offset and the length. So this is the offset and this is the length, and it's just going to return whatever is in memory at that point. Reverts is exactly the same. So reverts flavor is used for error messages. So this is the normal halting function. Now this one is interesting because I think it was kind of added here a little bit awkwardly. If W is revert, then we still get the output buffer, but we also sort of null the state, so to signify that it's kind of like an exception, or in other words, that we want to help. It's a little bit weird that O isn't present here. It's not really a problem because both stop, return, and revert cause 0 gas. So the fact that gas isn't deducted since there's no O is not really a problem. But It's a little bit inconsistent. Great. And then the only other thing is we see this mu prime, and that's the same as mu, except we deduct gas. Oh, okay, so fair enough. So they're deducting it over here. Note that when we evaluate xi, we drop the fourth element I prime and extract the remaining gas mu sub g prime from the resultant machine state mu prime. So I think that's what's going on here. X is thus cycled recursively here until either z becomes true, so this is an exception, indicating that the present state is exceptional and thus the machine must be halted and any change is discarded, or until h becomes a series, indicating that the machine has reached the controlled halt. For the machine state, let's also have a look at KEVM again. So K is this language that allows you to specify programming languages, virtual machines, and programs. And it all begins with the configuration, which is the tree of stores of that particular language, machine, or program. And it's written in XML format. And so we can actually see everything here. There's Ethereum, some config values composed of EVM, and the network, which contains a bunch of accounts. This looks like it's transactions. This looks like it's the block header. I think it's poorly named. And the call state. So this is anything that is pushed onto the call state stack when you make a call, a message call, and popped from it and restored as soon as the message call ends. So here we have some environmental data, and then here we have all the machine-specific stuff. And as you can see, it's one-to-one with what we're about to do. So there's the stack, the memory, the program counter, gas available, memory used, call gas. And here we have gas available, program counter, memory, the amount of memory used, and the stack. The memory contents μm are a series of zeros of size 2 to the 256. So technically it's not infinite. For the ease of reading, the instruction mnemonics written in small caps should be interpreted as their numeric equivalents. For the purpose of defining Z, H, and O, we define W as the current operation to be executed. So if the program counter is smaller than the code size, it represents the code at that program counter. And if it's greater than or equal to, we just implicitly add stop after code ends. We also assume the fixed amounts of delta and alpha, specifying the stack items removed and added, both subscriptable on the instruction and instruction cost function C, evaluating the full cost and gas of executing the given instruction. So all of that, delta and alpha, is defined with every single instruction in Appendix H. So this will represent how many stack elements it eats, the parameters of that instruction, and the other one, how many it pushes. We've already discussed this. This states that the execution is an exceptional halting state if there is insufficient gas, if the instruction is invalid, and therefore its delta is undefined, if there are insufficient stack elements, if a jump or conditional destination is invalid, the new stack size would be larger than 10, or state modification is attempted during a static call. The astute reader will realize that this implies that no instruction can, through its execution, cause an exceptional halt. Also, the execution is in an exceptional halting state if the gas left prior to executing an S-store is less than or equal to the gas stipend G call stipend 2300. Okay, fair enough. So if we have less than 2300 gas, we cannot make S-stores. We previously used D. So remember I said D is the set of jump destinations. So let's well define it as the function to determine the set of valid jump destinations given the code that is being run. We define this as any position in the code occupied by a jump dest instruction. All such positions must be on valid instruction boundaries rather than sitting in the data portion of push operations. Okay, so if you ever have a look at EVM bytecode, it's a bunch of instructions, but there's one exception. Whenever there's a push, the next bytes do not represent executable instructions. So push operations range from 1 to 32. So for example, push 2, the next 2 bytes would not represent executable instructions. All such positions must be on valid instruction boundaries rather than sitting in the data portion of push operations and must appear within the explicitly defined portion of the code rather than the implicitly defined stop operations that trail it. Formally, we define D through this recursive function, which initially the index is set to 0. And the way it works is if we reach it's kind of like a reduce, like a fold. So if we reach the end, it's just the empty set. And until then, we do a union reduction, union operator. If it's a jump destination, we add it to the current accumulator. And if it's not, then we look at the next instruction. What does the next function do? Well, usually it just looks at the next instruction. But if it's a push instruction, then we can think of this, we can take this 2 and move 1 over here and then 1 at the end. And so we have I plus 1 that looks at the next instruction. And then we have W minus push 1. That's going to tell us how much more than push 1. And then we have 1 for push 1. The normal halting function H has already been defined. The data returning halt operations, return and revert, have a special function H return. Note also the difference between the empty sequence and the empty set. Okay, so we're reaching the end of at least today's lesson. Execution cycle. Stack items are added or removed from the leftmost lower indexed portion of the series. All other items remain unchanged. In other words, delta is how much we're adding minus how much we're subtracting. So the length of the stack needs to adjust. For everything, for all stack limits between 0 and how many we're adding, they just get assigned according to the instruction semantics in Appendix H. And for all other ones, they get moved down by delta. The gas is reduced by the instruction's gas cost, and for most instructions, the program counter increments on each cycle. For the 3 exceptions, we assume a function J, which evaluates to the according value. So here we're using the n function to increment the program counter, which we saw above, with the exception of jump and conditional jump. So this next function, as we remember, also takes care of the push instructions. In general, we assume the memory, accrued substate, and the system state do not change. However, instructions do typically alter one or several components of these values. Altered components listed by instructions are noted in Appendix H. That's it. We've discussed chapters 4, 6, 7, 8, and 9. And the only thing remaining is Appendix H. Okay, so the last 2 sections, Appendix G. The fee schedule G is a tuple of scalar values corresponding to the relative costs of a number of operations that a transaction may affect. So there's the R's here are refunds. For example, refund given when the storage value is set to 0 from non-zero is 15,000. Refund given for self-destructing an account is 24,000. But most of them are definitions of some constants. There was a recent EIP, something like 2929, but it's probably different, where they added the concept of touched accounts and touched storage keys. And now, for example, if you S-load a brand new storage key, in the past you always paid, regardless of whether it was accessed before or not, you paid 200 for an S-load, then they increased it to 800, now they changed it. So the first time it's 2100, but then the next times it's only 100. Appendix H, virtual machine specification. When interpreting 256-bit binary values as integers, the representation is big endian. So I assume you're familiar with these encodings. The way I remember it is it's actually oppositely named as it should be. So big endian actually means that it starts with big values when they're interpreted, and it actually ends with little values, or I should say their interpreted values. In fact, everything on the EVM is big endian. I don't think there's anything that is a little endian. Solidity, for example, if you use bytes 32 or use a string, it will actually place that at the beginning of the data segment, but addresses, uints will be placed at the end of the data segment. When a 256-bit machine data is converted to and from a 160-bit address or hash, the right words, 20 bytes are used and the left 12 are discarded or filled with zeros. So in other words, it's saying if you call an address that has more than 166 bits, then the leftmost bits, however many there are, 96, will be ignored. So mathematically, it's an operation of modulo 2 to the 160. H.1, gas cost. The general gas cost function C is defined as, so this is the function that we saw earlier in the execution model. We saw that right here. So we saw that this gets subtracted. And now they define it as the new memory usage minus the old memory usage, so the diff in the memory usage. Now this is quite interesting. So the memory usage, you pay a constant for every byte. Or sorry, this is actually in words. So this variable is in words, therefore this variable is in words. Constant, and then you pay a squared divided by 512 and the truncated division. So what this says is that after a certain amount of words, in particular like 512, it's actually going to grow quadratically. So you can, with a little bit of abuse of notation, you can think of this as a polynomial, and so obviously for large values of a, it grows quadratically. Memory doesn't shrink. So if you mstore, which is to write to memory, so you mstore at position 10,000, a non-zero value, and then you mstore at the same position a zero value, and then you call msize, which is another instruction. It's not going to shrink, so it's still going to show you 10,000. Or since these are actually in words, it's going to be the number of words that you need to contain 1,000 bytes. So the nearest word boundary is 1,024, and so you need 32 words. So that's the memory usage component, and then we're adding this this gas function. So if the instruction is a block hash, it's a constant. Then we partition a subset of the instructions into G0 through G high. These are all very low. Even G high is, what's G high? Conditional jump. It's not a lot of gas, to be honest. It's pennies. This is the stuff that takes up the majority of the gas. So obviously there's S load, which will be defined later. Ketchak, so Ketchak has a fixed cost, and then it has a cost per word, again, rounding up. Create 2 has a fixed cost as well as a cost per, so there's some hashing involved in create 2. Create itself is fixed cost, but you also have to pay for the contract creation transaction. So for all of the bytes in the call data, or as we by now know, it's actually not call data, it's the init script, and whatever that returns will be. So there's a subset of instructions that are call instructions. So call and call code were in Frontier in the very first version of the EVM, and then they added static call and delegate call. You can log stuff, so you can emit events, and there's a few others. So with that, let's read this. Note the memory cost component given as a product of G memory and the maximum of, so that's right here, and the maximum of 0 and the ceiling of the number of words inside of the memory must be over the current number of words, mu I, in order that all accesses reference valid memory, whether for read or write. Such accesses must be for non-zero number of bytes. Referencing a zero length range. So when can this happen? So this is, for example, if you use any instruction that uses memory. So for example, call data copy or code copy or return or revert, or I guess even create. And you pass in the memory offset as X, but then the length as 0. So that would be called the zero length range. Referencing a zero length range, for example, by attempting to pass it as the input range to a call, does not require memory to be extended to the beginning of the range. So here they're saying that the memory usage in that case will not grow. Mu I prime is defined as this new maximum number of words of active memory, special cases that are given where these two are not equal. Note also that CMEM is the memory cost function, the expansion function being the difference between the cost before and after. It is a polynomial with the higher order coefficient divided and floored, and thus linear up to 724 bytes of memory used, after which it costs substantially more. While defining the instruction set, we define the memory expansion for range function n, thus, right, so this is the number of words of memory that you're using. So, excuse me, the stuff that I've been talking about before. Another useful function is all but 1/24th. So this is roughly equal to 63/64 of n. H2 instruction set. As previously specified in section 9 execution model, these definitions take place in the final context there. In particular, we assume O is the EVM state progression function and define the terms pertaining to the next cycle state, sigma prime, mu prime, such that O of sigma mu AI is equal to sigma prime mu prime A prime I. Here given are the various exceptions to the state transition rules given in section 9, specified for each instruction, together with the additional instruction-specific definitions of J. So J was our jump function. Believe it was part of the N. Oh no, it was part of the mu prime PC definition assignment. So most of the time we just do next, which jumps over pushes, and in all other cases increments PC by 1. However, for jump and conditional jump, we will see there are specific overridden definitions. And it also defines the function C, the cost function. For each instruction, also specified as alpha, we already know what that is, the additional items placed on the stack, and delta, the items removed from the stack. So we're going to have, I believe, 5 categories. They're given by the first nibble. So zeros are stop and arithmetic operations. Tens are bitwise logic operations, environmental information, stack memory, storage and control flow, push, log, and system. I think that's 6. So without further ado, let's begin. All arithmetic is modulo 2 to the 256 unless otherwise noted. The 0th power of 0 is defined to be 1. Also, division by 0 is for some reason defined to be 0. So let's begin. Stop, halts execution. Add, takes two elements from the stack, adds them up modulo 2 to the 256, and places their sum on the stack. Mul does the same thing for multiplication, subtraction. Now division is interesting because it does truncated division. However, if the divisor is 0, then it just returns 0. So previously in Solidity, Solidity mimicked this behavior, unfortunately. So if you had some equation computing the amount of tokens you have to pay for a swap, and there was some division, and you were able to make the divisor 0, then you would end up paying 0 tokens, and you could steal the entire pool. So that was kind of a security vulnerability. So they changed that, and Solidity now reverts when dividing by 0. We have sdiff, which is the same as diff, except the values are interpreted as signed integers. Modulo, sign modulo, modulo addition, modulo multiplication, exponentiation, and extending signed integers. We also have a less than comparison that places true or 1 if the first argument is smaller than the second. Equality. So for example, Solidity uses this in its function dispatch. So it takes the first 4 bytes of the call data, and it does a big long switch statement in which it checks whether the method ID, the sig hash, the message.sig, is equal to any of the method IDs of the public entry points. And then if so, it jumps to that function. Is0 is also very important. Solidity uses this when it's making a call, in particular a high-level call. In that case, it'll check the return value. So calls always, most calls, they push one element of the stack, which is the, sorry, not return value, it's really the status code. So it's going to be 1 if it's going to be 1 if the transaction was successful and 0 otherwise. So here we might do is0 to find out whether or not the status code was 0. We also have an AND operation, or, XOR, not. They're not all 100% independent, so obviously bitwise operations may be able to be defined in terms of arithmetic operations and vice versa. But of course, the bitwise operations are generally a little bit cheaper than their generic variants. Byte, retrieve single byte from word. So this is actually, so this part right here is actually my code. There was a bug in the yellow paper, so I corrected it. We have left shift, right shift, and arithmetic sign shift. Catch-hack is a built-in instruction. We have access in the EVM also to some other hash functions, like for example SHA-2, probably the most famous and widely used hash function out there. Those are implemented as precompiles. So we saw here, if the address is 1, then it's a precompile called EC recover. If the address is 2, it's SHA-2. RIP160, ID just returns whatever you pass to it. And then they added some later ones as well for complex cryptography. And then I think Blake2 is also another hash function. In all other cases, we just execute the message call. These precompiles, their code is still the empty byte sequence, so they don't have code per se. However, there's some, these 9 exceptions to the EVM. So when you call one of these addresses, the semantics are actually fully laid out for each of the 9 opcodes in Appendix E. Address gets the address of the currently executing count and pushes it onto the stack. The Solidity equivalent used to be this. now it's address of this, because if this is contract type, you have to convert it to address. Get balance of the given account. Later on, they also added self-balance, which is slightly cheaper, and it allows you to get the balance of the current executing account. And again, they both place one value. This in Solidity is called tx.origin, it's called message.sender, it's called message.value. Call data load allows us to get one word from call data. For example, Solidity uses this again in its function dispatch. So it might call data load 0, gets us the first 32 bytes, and then it might like shift it so that it's at the end, or it might just use some logic to isolate the first 4 bytes. Call data size. So this is useful if you want to use call data copy. So if you want to copy the entire call data copy. Let's have a look at what call data copy does. So a lot of times it's easier to use this website than the yellow paper. Offset in memory, offset in call data and length. So if you want to copy the entire call data, you would pass the 0 here and the return value of call data size. Code size, get size of code running in current environment. I don't think I've ever seen this used. Code copy code running in current environment to memory. So this, I believe, is used in 2 situations. It's used, as we kind of already saw, it's used in the init script. So the init script generally has this form. We first do state variable initialization, then we run the constructor, and then the bytecode of the contract itself is appended. And we might do code copy with this to sort of put all of that in memory, and then return from memory the desired bytecode. The other case where it's used is contract creation on the EVM level. So if you create a new contract on the EVM level, so in Solidity you call new with a contract type, that contract's init code must be in the bytecode of the calling of the constructing contract. And so there, Solidity might use code copy to copy that init code to memory, and then use create to create a new contract with that particular init code. Turns out we have access to the gas price of the current transaction. So this has been a little bit overridden in EIP 1559. The yellow paper is not up to date to 1559. External code size is extremely useful. Solidity uses it every single time you make a higher level call to ensure that the contract exists and that you're not just getting success because there's an empty account and you're just sending call data to it, and so it's just going to give you success. If you make a low level call, you should use external code size. OpenZeppelin provides a library called address. If you use that library, you can call address.isContract, which will use assembly to get the code size. And last but not least, this should be probably used in data validation. So if you're, for example, having a constructor and it has some references to some other network contracts, you should probably check that those parameters correspond to actual contracts in the EVM network. External code copy, I don't think I've ever seen this used. There's also external code hash. I don't think I've ever seen this used. And then they also added sort of this, as we already know, the output buffer called return data. And so this allows us to copy from the return data. And if we want to copy everything, we have to use the return data size. So this is used by proxies, as we already saw. Once the delegate call returns some data. We don't know, it's going to have dynamic length, variable length. So there we just, don't place anything to memory directly, and we're going to access the return buffer, the output buffer, to copy the entire variable length contents to memory so that we can return it, so that the proxy returns exactly the same thing as the implementation / logic contract. We also have the block hash, which allows us to get one of the last 256 block hashes. Of course, we can get the current block hash because the current block hash includes, and I'll show you right here. The block header will include, for example, the state root and the transactions root and the receipts root, and we won't know these until we fully execute all transactions in the block. Next, Coinbase. So this is a term inherited from Bitcoin. It signifies the address of the miner. So here it's get the current block's beneficiary, also could be called recipient's address. This used to be called in Solidity now. Now it's called block.timestamp, block.number, block.difficulty. I think there's block.gas limit. There is block.chain ID. And we have self-balance. Chain ID is useful because it allows us to differentiate transactions to different EVM compatible networks. So chain ID is actually also included as part of the transaction that is being signed. And so if I send a transaction on Ethereum, I know that I can't reuse the same transaction, or somebody else can't reuse my signature for a different network, like, for example, a test network, but it could be another valuable network because they'll have a different chain ID. So this was also added in an EIP right after sort of Ethereum Classic forked, and it's called replay protection. Stack, memory, storage, and flow operations. So we can pop, we can mload, mstore, mstore8, sload, and store. The gas computations for store keep getting more and more complex by the day, so we won't discuss that right now. The TLDR is that you first pass in the key and then the value, and the storage of that key becomes the value. So jump is very simple. Jumps to the first, to the sort of program counter in the first stack element. Conditional jump is the same thing, but it also looks at the second stack element, and it jumps only if it is 1, if it's true, or any other value, not 0. Program counter returns the current program counter. M size, we just multiply how many words of memory we've been using times 32 to get the number of bytes. Finally, gas left, amount of available gas. I believe this is called gas left in Solidity, and we can only jump to jump destinations. So there's been some criticism of the EVM in the sense that these sort of take elements from the stack. It would be much better if there was some static jumps that would not depend on the execution environment on the stack, but would be sort of fixed jump targets. This would make static analysis and other forms of analyses much easier, but it is what it is. So we have push 1 through push 32. The way these work is rather simple. So here. So the executing bytecode, whatever we return from the init script, is a sequence of instructions, but there's one exception. Whenever you have a push, then the next that many bytes will not be instructions. So these will be sort of the data segment of the push, and they will never be executed as instructions. So this allows us to push data onto the stack, into the contract. So there's many times this is used in Solidity. Obviously, the function dispatch, there's going to be a push for with the various method IDs to check if one of the method IDs corresponds to the message called sig hash. In Solidity, if you use the constant or immutable keyword, then those variables will be placed into the bytecode in terms of push instructions. So those variables will not be stored and loaded. So you'll actually save a lot of gas. The catch is that they have to be static. They can never change. We can also duplicate elements, swap elements from the stack, duplicate them, log, and here we are. So let's get into the interesting stuff. So create is the one of the two instructions that allows us to create contracts on the level of the EVM. It is used by Solidity when you do new and a contract type. It takes 3 parameters. Let's have a look at what they are. So how much ether we want to send along, the offset in memory, and the memory length that will constitute the init code of the created contract that then gets executed, and whatever that returns is the pseudo-immutable code of the new contract. I say pseudo-immutable because it can be changed with a self-destruct. Create a new account with associated code. So the init code is the memory from the second parameter and with the length of the third parameter. The salt, which is used by create2, in this case is the empty set. And there's 2 preconditions. So the call depth must not exceed 10 to the 24, and the value or the endowment must be smaller than or equal to our current balance. We then call the contract creation function, and the value that gets pushed onto the stack is going to be 0 if there was an exception or revert, and it's going to be the address of the created contract if the create succeeded. We expand memory usage if we need to. So most of the time this won't happen because we'll already have some code in memory, so it'll already have expanded before. And it seems like the output buffer is also nulled. So if you make a call and then you do a create, you no longer have access to the output buffer of the call. Okay, so this is by far the most complex instruction. Let's have a look at the parameters. So gas is a little bit tricky because it can be sort of overridden. It's not always, won't always be the gas that is available for the call. The destination, how much ether we're sending. This is the offset in memory, the offset length. And then if we know the fixed size return value, we can sort of not use the output buffer later on. We can directly place whatever gets returned into memory. Okay, so again, it seems like the preconditions are exactly the same. In this case, we're going to put 0 if there was an exception, and we're going to put 1 or true if the call succeeded. We expand memory, and the gas cost calculation function is the most complex. So let's start at the end. So C extra represents sort of the semi-fixed, pseudo-fixed cost of the call. In particular, C extra is composed of C access, which is the new IP that charges more for accounts that are accessed for the first time in a transaction, and less if the particular account has already been accessed on a per transaction basis. C transfer is 9,000 if we're transferring value, and C new is 25,000 if the target is dead, so remember dead is either if it's an empty account or if all of its components are empty, and at the same time we're transferring value. In other words, we have to create a new account. So that's C extra. Now, C gas cap is the most important function. Yesterday, I kind of thought about it, and it seems to me that this case cannot occur, and I've raised an issue in the repository. They haven't responded to me since yesterday. I'll try to explain why I think it's not possible. So if the gas available is at least the sort of semi-fixed amount we have to pay for the gas, then there's some algorithm for computing the gas cap. The gas cap can be thought of as the temporary call gas, because the actual gas that is available in the call, in the message call function, is C call gas. However, C call gas is just equal to gas cap if we're not transferring value. And if we are transferring value, we do have to pay for this 9,000 right here, but we also get a stipend of 2,300. I'm guessing this is for reentrancy protection, but it's honestly a pretty weird algorithm. So let's see if this case is ever possible. Well, this case would occur if we negate this inequality. So we get gas available is smaller than C extra, but the amount we have to pay for the gas is C call. Gas cap is non-negative. So if gas available is smaller than this, then it's also smaller than this. And if it's smaller than this, then it's smaller than the C function. I'll look it up. So right now, we're computing this. And if it's smaller than this, then since this is non-negative, it's also smaller than C function. But in that case, in the message call semantics, in the execution model semantics, even before the opcode gets executed, so even before here, we'd have an exception since we don't have enough gas. So it seems to me that case is not possible. However, I have yet to confirm that. So we also have call code, message call into this account and then alternative accounts code. So this is the old version of delegate call. Now, what's the difference between delegate call and call code? So the difference is that call code also allows us to send value, to send ether, and in the new sort of call frame, the message.value will be whatever we send. Delegate call does not allow us to send ether, and so the message.value or the EVM, the call value, will actually be the call value of the previous call. So this is very important. And the second difference is that the sender in a delegate call, so the message.sender in Solidity, caller in EVM, will persist. So it will be the caller of the previous transaction, while in call code, it's actually going to be the contract executing the call code. So both of these make delegate call much, much more useful for proxies. And delegate call is really only used for proxies. Any contract that has a delegate call can be thought of as a proxy in some sense. So the reason it's more useful is if you have a contract that's a proxy and it delegates call into an implementation contract, then if the implementation or the logic contract uses message.value, it will represent the value that is being sent to the proxy. So remember, the proxy holds all the storage and all the ether. And ideally, the logic contract has no storage, no ether, and only has the logic code. So the value will be whatever is sent to the proxy, so the logic contract will execute correctly. And also the message sender in the logic contract will be the original sender to the proxy, and so the logic contract will execute successfully. Return, halt execution, returning output data. So I think we've already seen this before. Offset in memory and memory length. And we define it right here. This has the effect of halting the execution at this point with output defined, see section 9, and we expand memory usage if necessary. Create 2 is a new opcode that allows us to create contracts in a slightly different manner. So the algorithm for computing the address is the only thing that's changed. And you can look it up in EIP like 159 or something, the exact semantics there. It also takes in a salt. Static call is also a new instruction, and it's the same as call, except we cannot send value, and the last argument of theta is bottom. So what that means is this argument is bottom, and so what that means is we're not allowed to make any state modifications. Solidity uses this function, this instruction, for calling external view functions. Revert is also a relatively new instruction, so we already know it's something between sort of an invalid instruction and a return. So it halts execution, it returns false as status code of 0. All state changes in the current call frame, the current message call, are reverted. And if you're using Solidity, then probably deeper calls will also be reverted. However, not all gas is consumed, so it doesn't consume all gas, unlike invalid. And most importantly, it allows us to specify an error message. So it allows us to specify a return value. And last but not least, we have self-destruct. So we add the current account to the self-destruct set. At the end of the transaction, the account will be nulled. We also say that we've accessed this account. And it takes one element from the stack, and that's actually going to be the destination, and it immediately sends ether to that destination, all of its ether. So the ether transfer happens immediately, but the nulling of the contract happens at the end of the transaction. So here, R is the first stack element interpreted as an address, and if it's the empty set, and at the same time there's no balance in the current contract, then it just remains the empty set. If it's not equal to the current contract, then we send its balance there. And if it is equal to the current contract, then it will just be 0 for now. The balance becomes 0. And the cost for self-destruct, you can read this on your own.